Welcome back to the deep dive. We dig into complex sources, pull out the key research, and give you the knowledge you need. Today we're tackling a really fundamental challenge in mathematics, finding exact answers for polynomial equations. Now, you probably remember from school, second degree equations, quadratics. They're pretty easy. There's a formula, you plug things in, you get an exact answer. Simple. But jump up to degree 5 or anything higher, and suddenly classical math just hits a brick wall. They're considered, well, unsolvable, not by approximation, but by exact methods using standard tools like roots.
Right, and that wall isn't just an inconvenience; it's a fundamental limit in classical algebra. Once you hit that point, the standard approach flips entirely. You move to numerical approximations. You get answers that are close, maybe really, really close, down to many decimal places, but they always have some rounding error baked in. They aren't perfectly exact.
And we're not just talking abstractly today. We focused our deep dive on a specific, really challenging equation, a 13th degree monster. I mean, it starts 6 by 13 nodes, and there are 12 more terms. Huge coefficients, some positive, like plus 78 by lefts, and negative, like 100 by lefts. It's a beast.
It really is. That's the kind of problem that classically you just throw approximation methods at and hope for the best. So, our mission today is to really unpack a claimed breakthrough, Ezouidi's theorem. This is a methodology that says it can deliver exact symbolic solutions, real, perfect answers, not approximation, even for something this complex. And it claims to do this precisely where classical algebra says, nope, can't be done.
Okay, that definitely sets up a fascinating conflict. So before we get into how Ezouidi's theorem supposedly works, let's quickly revisit that wall. Why does classical math say this 13th degree polynomial is unsolvable?
Well, the big name here is Abel's theorem. It's been a cornerstone for generations, defining the limits of what we call algebraic solvability. And solvable here has a very specific meaning. It means, can you write down the root using a finite number of steps involving basic arithmetic, add, subtract, multiply, divide, and crucially, radicals?
Radicals, like square roots, cube roots, that kind of
Exactly.
thing.
Square roots, cube roots, fifth root, any kind of nth root. Abel's theorem proved that for general polynomials of degree 5 or higher, there just isn't a universal formula like the quadratic formula that uses only these operations. It doesn't exist.
Why degree 5? What makes that the cutoff degree?
That dives into the Coca-Cola theory. It's pretty neat, but the simplified idea is about the structure of the roots, how they relate to each other, how they can be swapped around or commuted. For degrees 5 and higher, that structure becomes too complex to be untangled using just radicals. The underlying mathematical group structure isn't solvable in a specific technical sense, which blocks finding that kind of closed form radical solution.
So the traditional toolbox just fails. And you're pushed towards approximation. But hang on, the sources on Ezouidi's method explicitly state it excludes classical methods, including Ezouidi's theorem. That sounds huge, like finding a way around a fundamental mathematical law. How does the source material say it gets past that?
It's a key distinction they make. Ezouidi's approach doesn't try to find that one size fits all radical formula that Abel proved impossible. Instead, it's described as a systematic process. It transforms the original difficult polynomial into a different, simpler form that is exactly solvable. The sources argue this shows that even polynomials whose roots can be expressed with radicals might not be solvable using classical methods. It suggests the limitation was in the approach, not necessarily the polynomial itself.
Okay, that's a critical point. And for you, listening, this matters because of precision. If you're, say, designing something in quantum physics or maybe doing complex structural engineering calculations, getting an answer like 4.000001 when the real answer is exactly 4, that tiny error can sometimes cascade, it can matter a lot. You often need the absolute certainty of the exact symbolic answer. Approximation, however good, isn't always enough. All right, let's get into the method itself then. Ezouidi's theorem. You said it's a process, not just a formula. How does it actually work on this massive 13th degree equation?
The central idea seems to be about structural transformations. Instead of tackling kx head on, the method focuses on calculating a whole sequence of new coefficients. Let's call them x. These x values then define new related polynomial, let's call it ARX, which crucially have the exact same roots as the original.
Huh. So it's like finding a different way to look at the problem, where the monster suddenly seems tame.
That's a good way to put it. And the process to find these ESCO values is recursive. You don't get them all at once. You calculate them step by step. The formula to get a specific writer is complex itself. It involves things like binomial coefficients, from combinations, and importantly, uses the results from the previous steps. To find values, you need the values of SQR and so on. We've already calculated.
Okay, so you work your way up, calculating these EDS values from $2 right up to sekel and no 1. For our 13th degree case, 1 is 13, so that's 13 steps, calculating 13 of these sextile coefficients. That sounds incredibly calculation heavy. Are we just trading one kind of complexity for another? Did they have to run supercomputers for days just to find these sextile values?
Theoretically, the calculations could be immense. But here's the kicker, the real aha moment that comes out in the source material. When this recursive process was actually applied to that specific 13th degree polynomial we mentioned, the results were frankly stunning. The vast majority of those statistical efficiencies, they just simplified down to zero.
Zero.
Right.
That's actually shocking. We started with an equation with 13 terms, all non-zero, and this complicated recursive calculation somehow made them all zero. Was that just a lucky fall of this particular polynomial, or is the theorem somehow designed to find this kind of hidden simplicity?
The sources suggest it's not luck. It's inherent to the method's power. It seems the recursive structure systematically identifies and eliminates terms that turn out to be, well, algebraically redundant when it comes to finding the actual roots.
Okay, let's get specific then. Which coefficients went to zero? Which terms disappeared?
The source material lays it out clearly. The coefficient through Zeller, those correspond to the 612 down to 6 terms in the transformed polynomial, they all come out as zero. Also, the coefficient to the 6t6 Ferdal, that was 0, 2. And then further down, 6LRS and even 612L are all zero.
Okay, so out of 13 potential coefficients in this transform polynomial, only 2 ended up being non-zero. Besides the leading $6 term, of course, what were the survivors?
The ones that remained were sum and unvary, which goes with the 6th knowledge error term. That calculated out to exactly 136 terms. And the other was the $6, the coefficient for the plain 6 term, for $6. That came out as the exact value, 133 times 1312. A large number, but precise.
So let me get this straight. That original monster equation with all 13 terms, after applying Ezouidi's theorem, it transformed to this incredibly simple looking thing. Px pi x are reached by 13 plus 136 by 7, 133 times 13 dollars exabytes.
And that simplification is the whole key. Takes a problem from the classically unsolvable category right into something we can actually manage algebraically
Yeah.
and solve exactly.
Okay, fantastic. Let's solve the simplified version then. Looking at it, the first step seems obvious. Every term has a $6.
Right. So you can immediately factor out in $6. That gives you $6 plus 136 by 6 plus SLR. And straight away that tells us one rule. For the whole thing to be zero, either $6 or the part in the parentheses is zero. So map the $F is our first guaranteed exact rule.
Okay, one down. And the source material also mentions something interesting, that 6.01 would also constitute a root with multiplicity 5. That's quite specific. How did that come about?
That detail seems to emerge from the analysis within the theorem's application, likely related to properties of the original polynomial's coefficients, or structure, revealed during the transformation. That's 6.1 and 6.15 terms. That accounts for 6 roots.
6 roots. So the remaining 7 roots must come from that factor left inside the parentheses. 6 file plus 136 by 6 plus $6.
Exactly. You need to solve that equation for the rest of the roots.
Now, $6 dollars and $6. It still looks a bit scary, but wait. 6 by $6 is just 3 splitting $6. This is actually, it's like a quadratic equation, but for $6 instead of $6.
Precisely. If you just make a little substitution, say let last by 6 mol, then the equation becomes $20 plus 136.5 plus SL3. And that's just a standard quadratic equation in linear algebra. You can solve that using the good old quadratic formula.
Right. And since we know the exact values for the coefficients, the $136 and that big successful value, we can get an exact symbolic solution for i's, which is $6.06.
Correct. You apply the quadratic formula, do the algebra, and you find the exact values for $6.
And then presumably you take the 6th root to find $6, which will involve complex numbers.
Yes. Taking the 6th root will give you the remaining roots, expressed in terms of complex multiplications. When all the dust settles, the source gives the final exact symbolic expression for these roots. They involve the number 13 $3, the square root of 503 and $3, and 1.
You know, for centuries, there have been these math problems that were just, well, unsolvable. They were like these giant walls that even the greatest minds couldn't seem to break through. But what if the secret wasn't to break the wall, but to find a really clever way around it? Well, a new theorem claims to do just that, cracking the code on a whole class of these supposedly impossible equations. So think about it like this. On one hand, you've got simple polynomials, right? The kind you see in school. Finding x is like using a simple key for a simple lock. But then, on the other hand, you've got these high degree polynomials. These are intricate, complex locks that have resisted a universal key for centuries. The big challenge wasn't just finding an answer, it was about finding an exact one, a perfect key. And for a very long time, the mathematical world just said, nope, it's impossible. Okay, so what are we actually trying to find here? In the world of polynomials, the whole goal is to find the root. It's that one specific value for x that makes the entire equation balance out perfectly to zero. It is, quite literally, the solution to the puzzle. All right, here's our game plan for today. First, we're going to look at why this problem was even considered unsolvable in the first place. Then, we'll meet the new theorem that's challenging all of that. We'll peek under the hood at its recursive engine, watch it reveal the exact roots, and finally, we'll connect it all back to why any of this actually matters in the real world. All right, let's dive right in. Section 1, the unsolvable problem. We're going to look at this historical barrier that honestly stood for almost 200 years. For the longest time, the consensus in the math world was pretty clear. You just couldn't create a single, neat formula to find the exact roots for these really complex polynomials. The best you could ever do was get an approximation, a number that's close, but not quite perfect. And look, this wasn't just some wild guess, it was actually proven. There's this thing called Abel's impossibility theorem, and it basically put up a giant mathematical wall. It stated that for any polynomial of the fifth degree or higher, there's just no general formula using only basic arithmetic and roots, what mathematicians call radicals. So for nearly 200 years, this was a dead end, full stop. So that brings us to section 2, challenging classical algebra. How do you possibly solve something that's been declared unsolvable? Well, you introduce a totally new idea, and in this case, it's a theorem from Professor Mourad Sultan Ezouidi. Now, what's so cool about this is that the new theorem doesn't try to just smash through the rules of classical algebra. Nope. Instead, it claims to have found this really clever way to just go around them. It's a structured process that basically bypasses those old roadblocks, promising to deliver not just close enough answers, but precise, totally exact ones. Okay, so how on earth does it actually work? That's what we're getting into in section 3, the recursive engine. And it's all about systematically making the complex, well, simple. I want you to think of it kind of like a translation machine. You take the original numbers from the polynomial, those are its coefficients, and you feed them into the theorem's special recursive formula, one after another. For each old number you put in, the formula translates it into a new one, which we'll call an S value. And you just do that again and again until you've got a whole new set of numbers. So the output of this whole process is a brand new set of coefficients. And these new numbers, they're going to form a much, much simpler equation. So let's actually watch what happens when we run our big, scary 13th degree problem through this thing. Okay, the engine is fired up. The very first S value it spits out, 0. The second one, also 0. In fact, the first 5 calculations all come out to 0. Now this is where the magic really starts to happen. See, a 0 coefficient means that part of the equation just disappears, vanishes. And then on the 6th calculation, things change. Boom, we get our first non-zero value, 13 to the power of 6. This is a crucial piece of our new simplified puzzle, so let's hang on to that one. So the process keeps chugging along, spitting out more zeros, which means more of those complicated terms are just vanishing. And then we get one more critical value. S11 is negative 13 cubed times 13 to the 12th. That's the second and final piece of the puzzle we're going to need. So let's just pause and think about what just happened here. Out of 13 brand new coefficients, only 2 of them were non-zero. All the others, they're 0. We've basically just erased almost all of the problem's complexity, leaving us with just 2 key numbers. That is the absolute heart of this simplification. And all of that brings us to the big payoff in section 4, revealing the roots. This is that aha moment where we get to see what all that powerful simplification actually did. All right, let's take one last look at our opponent. This is that intimidating 13-term monster we started with, the one that classical algebra said nope, can't be solved with a neat formula.
And here's the result. The true power of this theorem is in what's missing. That huge, complex, 13-term monster completely collapses into this beautifully simple 3-term equation. And it's built using only those two non-zero s values we found earlier. The unsolvable has just become solvable.
And from that super simple equation, we can now find all 13 roots. It turns out one of them is exactly 0. The other 12 are complex numbers. But here's the crucial part. Every single one is derived from an exact symbolic formula. We're not talking about fuzzy approximations or rounding errors here. These are the precise, definitive answers. Okay, so we've got an exact answer. That's cool and all, but why does it matter so much? That's what our final section is all about. Why this matters. Why go through all this trouble just for perfect precision? Well, it matters because in really high-stakes fields, close enough can be the same thing as completely wrong. Think about it. In physics, one tiny error in modeling a quantum state can throw off an entire simulation. In engineering, a small miscalculation in analyzing a signal could be the difference between a system working perfectly and failing catastrophically. And in something like cryptography, the security of our data depends on the absolute rock-solid predictability that only exact math can give you. See, approximations create uncertainty, and uncertainty is where things break.
And it's really important to get this. This method isn't just some one-trick pony. It's not a solution